separate monitor, you can also like bring up the stream. I can send you the link. Chat.
I do have a separate monitor, but I think for now,
Yeah. If you need it for a talk, it's fine. Also, I'm going to record this. Okay, great. Okay, it looks like we have a good number of people in the stream.
yeah.
Hi everyone. We'll get started on the hour, so just a few more minutes. Okay, guys, so we'll get started. So, welcome everyone. Today we're very excited to have a presentation and a workshop from QBraid. So QBraid is a startup company that got its roots in MIT and Dartmouth, and they're pretty unique among the companies that are, doing the workshops this week in that they're kind of a platform to kind of integrate all the quantum computing languages together. And they have very unique features, as you will see later. And today we're very excited to have Kanav Setia, who is a co-founder and CEO of QBraid. So just a little bit about Kanav. So Kanav did his bachelor's in aerospace engineering with a focus in robotics. After his undergrad, he spent 4 years in a semiconductor fabrication facility working on the design and development of MEMS, which are micro electromechanical systems. And then after that, he went to Dartmouth for a PhD in experimental physics. When after his second year, he switched to theory. And then for the past 5 years, he has focused on quantum simulation algorithms, contributing to both open fermion and discrete chemistry. So, but yeah, without further ado, let's let's hand it over to Kanab and hear what exciting things QBraid is working on and how you can like learn from that. Okay, take it away, Kanab.
Thanks, man. Yeah, I'm super excited to be here telling all of you about QBraid and what we've been doing. Um, so the idea of QBraid is basically to take away all the pain points that people may have while trying to get into the field of quantum computing. And as you may all know, that there's just such a high entry barrier. And that's where we wanted to take away all those teeny things that stop people to from getting started in quantum computing. So actually, I'm gonna turn off my video because that slows my computer quite a lot. So, okay, now it should be good. And let me actually share my full screen rather than, yeah, there you have it. So here, this is the website. Just go to QBraid.com and you'll see that you land on the home page. And now you just click sign in and we've got your shortcuts here that perhaps will make sense a little bit later. Otherwise, you click on my QBraid. And before that, let me quickly show you. If you click on sign in, my QBraid, you're taken to creating your account page. You just put down your email. Let's say hello@qbraid.com, and you pick a password. And if you have an access key, you put an access key. The access key gives you access to a little more compute power than we make it already available. Then you click on terms and conditions, agree to that, and then you just click create account and you're good to go. And if you do that, you're taken to this page. And so this is your home page. Yeah, and so here are all your tools available on QBraid. So this QBook is a place where you could come and learn. So if you click on, let me see, yeah. So if you click here, study or write, you will be taken to a page where you have multiple courses available. So this is basically a platform for learning quantum computing. And as you can see, we currently have 3 different courses available. And as we grow, more people will be making their courses available on QBraid from which you will be able to learn. Let's say you want to learn Cube from Cube's course, which is one of the course that we developed in-house. So Andrea Coladangelo, who's a PhD from Caltech and a co-founder of QBraid, along with Jason Nikes, myself, and Eric Weiss contributed to making this course. You'll see Andrea doing all the videos, video lectures. And the best part of QBook is it integrates a lot of interactive features. So for example, this is one of the widgets, and this shows how superposition of waves work, right? So you have 2 waves with different phases, and you can change their phases using sliders. And as you can see, if I take them out of phase, the superposition goes to 0. And if I bring them in phase, it yeah, so the superposition is much higher compared to the waves, right? And then you have your quantum circuits. And so far, if you count the number of clicks from creating your account to all the way running your first circuit, and this is basically how you run circuit. You just press play and you've just ran your first quantum circuit. And so this is where I want to emphasize this, we think is our biggest achievement so far, where like reducing the all the hassle that stands between you and running your first quantum program, right? And now the question is, okay, you just ran your first quantum program. Do you understand it? Well, if not, we've built the whole course for you. As you can see, we do not assume any background. So if you just know, let's say 10th grade of science and mathematics, you're in a good shape to get started. We would teach you all the background quantum mechanics you would need to know, all the basic concepts in classical computing, complex numbers, vectors, and then we teach you your first how to write your first quantum program. First we teach you qubits, measurements, single qubit quantum gates, and so on. And the whole course is built with a lot of puzzles in mind. It's really interactive. So let's say I go to, I want to show, for example, complex numbers. So if you go to complex numbers, you have your video lecture by Andrea Coladangelo. You've got your widgets that you can play with. And then let's see, problem statements. And so let's go to our writing your first quantum circuit. And as you can see, so first you will have a lecture, and the snippet from the very first page, now it's expanded into uh, one, one Python line at a time, with us explaining what that exactly does, right? And so again, at any point, you'll be free to change it, modify it. Okay, this is a quantum circuit with one qubit and one classical bit. You'll be free to change it and then modify it. So this runs. Now, if you draw it, it's a circuit with two quantum gates, right? So let's say I apply an X gate here. And then I run this thing. So now I have this thing, right? So here, our goal has always been to make it as simple as possible for you to learn quantum computing, right? Now you do that, you can run the simulation and so on. So another thing you can do is you can also run it on the actual quantum computing computer by IBM or other hardware providers, right? And let's see, is there anything left here? No, that's pretty much it from the QBook side. And then let's say, so another good aspect of QBook is that it works great on an iPad. So if you just want to learn like a book and run few circuits while reading it, feel free to use your iPad. It should work great. If it doesn't, write to us. I've checked it multiple times on my iPad. So it should work great. And then let's say you've learned quantum computing. Learn is a place to tinker, right? And then research is where you will build your projects, or this is mostly focused on researchers in quantum computing. Now, before I tell you about learn and research, I want to talk a little bit more about the homepage. Now, we just didn't want to be a place for quantum computing tools. We want it to be the place for quantum, which means all the exciting stuff coming in. For example, in quantum news, you will see it here. And pretty soon you'll see that there will pop up a submit an article button somewhere here, and you'll be able to submit all the exciting news in quantum computing industry, and then everybody will be able to see what you've submitted, right? And then you have your blog posts. So these are uh, the papers coming uh, from, so these are very recent paper from just yesterday. So one of the really coolest papers from yesterday was by this Google group, where they realized a topological ordered states on a quantum processor. For those of you in the quantum computing world, they would know that this is a super exciting result. And the best part is, again, this is built into QBraid. You just press view article, and you're straight up taken to the article, and this should open up. As I was telling you, yeah, so this is the paper by Google result. Now you can read it. Eventually, you'll see that we'll provide you the functionality of storing the papers into your home directory, and you'll be able to save these papers as well. And blog posts. So blog posts, one of the blog posts that I wrote in recent times showed up here. And we will be giving you a lot of functionality with which you'll be able to share the blog post that you want to share with the rest of the people, right? So basically, if you've done an exciting project in quantum computing that you want to share with the world, we'll provide you a functionality, and then you complete that and you'll follow couple of steps, and your article or blog post would show up here for everybody on QBraid platform to view, right? And this should be an exciting feature. We're working on it. Stay tuned. Uh, One quick feature that I'd like to mention is that we will be working to provide you a kernel behind the blog post. What that means is if you've written a quantum program along in your blog post, then anybody reading your blog will be able to run the programs that you wrote, which which I honestly think is pretty cool because it'll work just like the QBook that I showed you, that anybody will be able to read and play with all the stuff that you developed. And your upcoming events will show up here. You can see QC Hack is showing up here, and we'll be adding a lot more events to here. Again, there should be a submit button coming up in next few weeks or maybe a month or two, which will allow anybody to submit quantum events to QBraid platform. And so anyone who's using QBraid platform, the event would show up on their dashboard, and they'll be able to see, and they'll be able to register for that event, right? So that is cool. And then you would have a profile page where you would from where you would control how much compute power you have, right? So you can see that we're making available these compute resources to you, and then you'll be able to use access key to get more resources, or you can just reach out to us at request@qbraid.com to request a certain um, feature or more compute power that you may have. If you want to do exciting projects, just reach out to you. We'll work with you to make new features available on QBraid, right? So now let's go back to our tools. So as I was mentioning, learn is where a lot of the action would happen. So let me go to learn. Actually, let me restart. So yeah, so if you go to learn, you'll see it looks similar to, let me move this out of the way. It looks similar to this, and you'll be able to launch a QC hack environment, which is what we've made available for you guys. Once you launch that environment, you'll see that it loads up the first notebook page, and you'll be able to run circuits from here. Now, learn is a place to tinker, right? So you've learned quantum computing, you come here and you'll see we've created an environment just for you. And in this environment, you have Qiskit, Cirq, Pikewill, then AWS Brocket, Pennylane, PyTicket from CQC, and a lot more, and TensorFlow. All of these cool packages already pre-installed, and you can start using anything that you would like. For example, import Qiskit, bam, that works. Import TensorFlow, that works. So you can even do machine learning projects here, right? And yeah, you'll see that most of this stuff works pretty smoothly. And then on top of that, if you go to your file structure, so this is what you would have available, and you can start coding. and we've included the instructions for cloning a Git repository, right? And then if you want to run it on an actual machine, we've included the instructions for running it on IBM's hardware. So you can go there, and if you go to the files page, you would see that you'll get this repository pre-cloned into your uh, into your home folder. So here you have available to you a Qubes course. This is the same course that you saw on QBook, but now you can make a copy of it. Like I can make a duplicate copy of it, and I can modify it as per my wishes, and then keep a separate copy. So this is an important distinction. In QBook, we do not provide you functionality of saving your interaction with the course. It reads like a book. You do a bunch of stuff, but then book remains the same. In Learn, you have the capability of building your own projects, taking the stuff that is already available, like from Cube's course or Quince, and then using it in your own projects. On top of that, tutorials from AWS, Google, IBM are already pre-cloned. So if you're working on any project with, let's say, Qiskit or Circ, you need any help, you just go to IBM, you go to tutorials, and let's say you want to work in finance. You open one of the notebooks, and this should work out of the box, right? And yeah, so you could go here. Most of this stuff works. And that's basically the best part. So you want to do a, uh, a project in finance using quantum computing, you just come to one of these notebooks, you see the code that would help you get started, you just copy it. Let's say, for example, I could copy this and I could start building in my own notebook, right? So if I do that, and from here on, I could do basically um, whatever that's available, I could modify it and go from there. And then similarly, you have, these were IBM tutorials. You have tutorials from Google, Circ examples. These are Open Fermion tutorials, which is open source repository from Google to do quantum simulation. And then you have AWS tutorials, which again should work out of the box. So you can play with any of those. And let's see, QBraid tutorials. And then as I was mentioning, let's say you want to clone a GitHub repository, right? Let me see if I do article. Yeah, so let's say you want to use Git. So all you have to do is come here, click here, and so we've created a repository just for you. So this will be the repository that you clone and then contribute to your projects. So we'll be unveiling a challenge. It should be a relatively simple challenge when the hackathon starts. And you'll come here, you can create a fork, and then what you will do, and let's say you created a fork and you'll be contributing your code and project on that fork before doing a pull request. So once you fork, you want to bring this to QBraid. So you just go and copy this URL and, oops, where did it go? Yeah, you come here, you paste, and then cloning, there you have it. QC hack, there you go. So you'll see that the repository has been cloned, and you can start working here. Let's say I want to use Python, and I can start writing my project and import Qiskit, and there you have it. And then you build up your project here, and you, if you go to Git you'll see that this shows up here, and I'll be able to, um, so this is untracked. I make it tracked, I stage it, and then I can commit my changes, first commit, right? And then I'll be able to push or pull the changes from here, right? So let's unstage this because I don't want this. Hopefully everybody knows how the Git works. Otherwise, we're here to help. And one really cool feature of QBraid that we've been building is this code snippets. So this is not done yet, but expect that this should be more lively in the coming weeks, or hopefully before the hackathon starts. So the idea here is we're providing the most helpful quantum circuit snippets to you via, let's say you want to run a variational quantum circuit, or VQE, right? So you click here, you would see the code here. And let's say you want import statements for bracket. You'll see that this is here. You can copy this code, you can paste it. So basically, you'll be able to search a lot of the snippets. We're starting to build, you'll be able to contribute towards the snippets. There'll be a voting feature. And so, yeah, if you contribute a lot of code snippets, other people may upvote it, and the most helpful code snippets would come to the top. And this we think should be an amazing feature because now you wouldn't have to even go through the documentation for what you're looking for. You'll be able to just search it here. And based on the community feedback, the most helpful code snippets should come towards the top, right? So that's about Learn. Let me see if I missed any of the features. Boom. Python documentation. Yeah, so another cool feature of our platform is you also have Jupyter notebooks available. So if I go here and I paste this and I change lab to tree, it opens up the normal Jupyter notebook UI. And now I can go to, let's say, here. So this is the presentation I wanted to give to you. And if you come here, you can also present straight from QBraid. So the idea here is that if you go here, view, and you change to slideshow view, then you'll see that slides, this thing pops up. And once you've selected all the slides, um, all the cells that you want to present as slides, you can click here on the rise button, and this should bring up the presentation. So this will be the presentation I'll be doing for the next half an hour. But before that, let me see if I've covered all the other features. This is to do. So before I get started on presenting to you a little bit about Aloha Quantum World, which is similar to Hello Quantum World, let me see if I missed on any other feature. Stage commit. Yeah, so let's quickly talk about the research environment as well. So here, the idea is this works similar to the Learn environment, but here you have QBraid environment, QBraid Dev, and QC Hack, Qiskit Textbook, AWS Bracket, Xanadu, Pikewell, Qiskit, CircOpen, and Fermion. So all these different software development kits available in a separate environment. So all of the people who do research would know that managing Python environments could be tricky. So this is where we've created a research environment where we provide you sandbox environment, and you will be able to customize those, create your environment. The philosophy of research is that if you're working on a project, not only the code should be shareable, but your environment should also be shareable. So what that means is if you're writing a project, you can share the code through GitHub with your collaborators, but with QBraid, you will also share the same runtime environment. So if your collaborators, previously they would have had to create the same runtime environment. Let's say if you are using Mac and somebody else is using Windows, it could be really messy. So with this way, if both of you are using Qiskit for your project development, just go to the Qiskit environment and your collaborators will have the same environment as you. Another cool feature that we'll be making sure is Qiskit and almost everybody else, they are developing at an amazing pace, which means they come out with a lot of new versions very fast. And when they do that, things with the older version could break. And if you wrote code with, let's say, version 16, then there's a good chance your code will break while trying to work with the version 26 or something. So this is where we would manage all those environment issues for you, where with each new version, we'll create a new environment for you. So that your code, if it was running at any point, will provide you an environment and make sure that the environment stays there and it would always run, right? So far, let me just stop quickly and see if there are any questions. Ben,
Yes, so I think there were a few questions in the chat. Yeah, we can do a quick question and answer session
yeah.
for now. So let's see. Okay, someone asked, uh, could you tell them a bit more about the access keys? You know, how can one get them, and then what are they like used for, basically?
Yeah, so currently, if you create an account, we give you access to the QBook and the Learn platform, but not the research platform. So yeah, so Learn and QBook should be good for most of the applications. But if you're a researcher and would like access to the research platform, send us an email telling about your use case, and we'll provide you an access key and you'll be able to access research. One of the benefits of research platform is that it also provides more compute power.
Okay, and someone else asked if are these services offered for free, the QBook, Learn, and also Research?
Learn is not for free. Uh, QBook, we envision it to be free long term. Learn, I think there will be a base tier that we may start charging, but for now, Learn and QBook are being offered for free. So these are like alpha and beta releases. So they just start using and yeah.
And for research, if someone's doing quantum computer research and they want to explore QBraid, then you would offer privately this platform to them, right?
Yeah, of course. So if you have a specific use case, as I was mentioning that we've already installed TensorFlow. And so if you want to do some machine learning stuff and quantum stuff, TensorFlow Quantum is also installed that I forgot to mention in the QC hack environment. So yeah, if you're doing something that's compute intensive and it's a great project, and yeah, just submit a one pager, why it is cool, and we'll be happy to support you.
Cool. And someone else said, pretty incredible technology for the QBook, Kanav. Can you talk a bit more about some of the challenges you faced when writing a kernel for it and how you made it run faster than Jupyter notebooks? And also, will you be using the same tech for the blog posts with code?
Yeah, so those are the technical, I think, yeah, just write me an email and we can have a separate session. Those are the long topics. It'll be difficult. A lot of the stuff that you already mentioned, you're on the right track. Yes, we use the same kernel technology, but it's kind of hard to explain how we made it super fast compared to the Jupyter notebooks. Yeah, we'll be happy to chat outside of this talk.
So if you don't mind, then I guess can I post your email in the chat so that people have your contact information?
Absolutely, go for it.
Okay, yeah. I think that is all the questions so far. So we can move to the next stage, and then maybe people will have more questions during the second part, and then we can have another Q&A session at the end.
All right. Yeah, that sounds great. I'm gonna stop my video again. Let's get started. Aloha Quantum World. So here, what I want to do is present a very simple, whoops, there you go. So present a very simple quantum program um, to demonstrate how quantum computing is super different than classical computing. In the next 30 minutes, what I'll be doing is the first 15 minutes will be discussion about Aloha Quantum World, which is very simple program similar to Hello World in the classical computing world. So this should be accessible to almost everyone. Even if you are a 8th grade student, this should make sense. And the last 15 minutes will be spent on something which is super complicated and where I spent 5 years of my PhD researching. It is quantum simulation. So I don't expect you to understand most of it, but if you could get like a high level gist of how that works, like in an abstract manner, I think I would have done my job. So let's get started. Hello world. So the Hello World program was actually developed by Brian Kernighan in 1974. Its purpose was to be the simplest program for the language, a demonstration of the syntax, and to check everything is working correctly, right? So this was basically the time when you didn't have a screen, you didn't have like the fancy machines that we have right now. Computers were just like these boxes that you programmed and somehow so figured out whether things were working correctly or not. And then came the displays, and that's where a lot of components were coming together. So people wanted to develop a simplest program to make sure everything's talking to everything else. So here in Python has made Hello World super simple. You can just press Shift Enter and you can see Hello World. As simple as that. That tells me that everything is working, that the servers that are currently powering QBraid, they're working properly, all the network issues are going good. Similarly, we wanted to do uh, Aloha Quantum World program. And Aloha hopefully will make sense in a little bit. So if you do this, then you would see that if I don't pass any input, it always prints hello world, right? And now if I pass in quantum, let's see, it prints some hello world. Let's run it again. Whoops. There you go. So sometimes hello world, sometimes bye world. And so this basically, the behind the scenes, what's happening is we're using a qubit and putting it in superposition and then measuring it, right? And so before I talk about behind the scenes, you can see, okay, this seems to be behaving like I have a hello world, right? So before we understand the Aloha quantum world, let's write a little bit different program, which is classical in nature, and it's called hello by world. And the way it is written is if you pass in a bit value, which is 0, it prints hello world. If you pass in bit value, which is 1, it prints by world. So let's check it. You pass in 0, hello world. You pass in 1, by world. Okay, this seems to be working fine. And then I'm gonna write a program for bit flip. So what it does is you pass in a bit value, it just flips its value and return it. And then what I do is you can have the hello by world and you can pass in the bit value, which is 0. You can flip the bit value to 1 and then print the hello by world and run the hello by world program again. And you can see first hello world and then by world. here, what I'm trying to demonstrate is the bit in classical computing could only be 0 and 1, right? That means the only operation you could do to it is you could just flip the bit. Like if it's 1, you can make it 0. If it's 0, you can make it 1. Okay, so far so good. Now, let's write another program for coin flip. Now, the idea of coin flip is it just, if you run the coin flip, it just 50% of the time it returns 0, 50% of the times it returns 1. It's like a, yeah, coin flip, exactly like a coin flip. So once you have that, now I'm going to do something interesting. I'm going to pass in coin flip to hello by world. So remember, hello by world takes an input, the bit value, which could be 0 and 1. Now, if I do this and look, so sometime it prints hello world, sometime it prints by world. And here you could ask, oh wait, how is it different than Aloha Quantum World that I showed you before, right? Where Aloha Quantum World was printing hello world sometimes and by world sometimes. So behind the scenes, what I'm doing is you have a quantum circuit which takes 1 qubit and 1 bit. And then I put it in superposition if you inputted the quantum. And then I simulate it and then I measure it. And based on my measurement, if I get a 0, I print hello world. And if I get 1, I print by world, right? And if you do that, then you would see Aloha Quantum World, hello world. And if I put in quantum, hello world, by world. And now comes the interesting question. Okay, so it's basically like a coin flip. What's fancy about quantum? Why do we even need quantum if you could basically do everything that's possible in quantum with a coin flip? Well, turns out it's not as simple as that. So if you go back and think about the hello by world, you do a coin flip. So it's like coin flip. So this Hadamard gate, you can think of it as a coin flip. So basically, if I do the Hadamard gate again, it's me doing the coin flip again, right? And if I do that, now from classically, your intuition would say, if I have a hello by world, and then I do a coin flip, and then I do a coin flip, the output still remains random. I still should have hello world some of the time and by world other times, right? And now let's see what happens in quantum where I have basically 2 coin flips. And hello world, hello world, hello world, hello world. By world never shows up. So this sort of tells you that quantum, in quantum, probability works a little bit differently, where it wasn't like in a coin flip where you did a coin flip and it was either heads or tails, but it was one of those. It was never that it was heads or tails at the same time. In quantum, it's actually heads and tails at the same time. And turns out if you do this coin flip or the Hadamard gate in quantum twice, it sort of cancels out and it brings you back to a definitive state, right? And yeah, so that's basically superposition for you. And you can do a classical side and so on. So now if you do quantum, you would get hello all the time. If you go back and remove this extra Hadamard gate, then you would see if I'm doing it 5 times, sometimes I get by world, sometimes I get hello world. Right. So before I move on to quantum simulation, does anybody have any questions about Aloha Quantum World?
I think there was one question. So someone asked for learn. When I try to access, I get 500 internal server error. You probably did not fill out the login form. I'm wondering if there you have any idea what is happening. I think that's not really related to Aloha Quantum World, but
We can come back to it. I think it's posted in the Discord, and so Jared and Elliot, who are classical software wizards, should be there to help you out. Any problems you may face with the platform.
yeah. So you can just post your question in the Discord.
Yeah.
And they'll swing by later, I assume, to answer that. Yeah, but I think other than that, no questions on the Aloha Quantum World so far. Oh, someone said, can you explain why the use of two hand mark gates cancels the random behavior once again?
Yeah, so the answer, this is gonna sound not a great idea, but in quantum world, the probabilities for the general state of a qubit is represented by complex amplitudes, right? So just like you had coin, which 50% of the times it could have been heads, 50% of the times it could have been tails. In qubit, which is 0 and 1, you give out probability amplitudes from which you calculate the probability, right? And those probability amplitudes could be complex. And what ends up happening is if you apply certain gates in certain ways, those amplitudes cancel out and they give you a definitive state. So if you start with 0, you put it in a superposition, which is a coin flip. That superposition, yes, the outcome looks similar to coin, but underneath the mathematical abstraction or the physical process is very different. And it allows for for canceling of the amplitudes, which means you would get a definitive state out of applying to Hadamard gate. Does that answer your question? I would say go through QBook. A lot of these questions would make sense if you go through. We teach all of this. What is a Hadamard gate and what is the general state of qubit in QBook? So all those things, and you will also learn complex numbers. Basically, you'll be able to answer this question yourself after going through QBook.
All right, someone else asked, can you also basically recreate the Hadamard gate effect in the classical coin flip?
No.
So I mean, like the double Hadamard gate effect. I guess they're asking, is it equivalent to a classical coin flip?
Not that I know of. So the basic intuition is you do the coin flip twice. There's no way you're gonna. So if you start with heads and you flip a coin, right now there's a 50% chance of heads or tails. You flip it twice, there's no way you're getting tails back, right? So in quantum, you started with 0, you put it into a superposition of 0 and 1, you apply another Hadamard gate, and it canceled it out, and it gave you 0. In coin flip, let's say you start with heads, you do a coin flip, now you're going to get heads or tails with 50% probability. You do another coin flip, you're still going to get 50% times, 50% chance heads, 50% chance tails. You're not in any way going to get heads back. Does that make sense?
Yeah, I think there's some discussion in the chat, but I think I think people are answering the questions basically as well. I think that's all the questions. But yeah, if you have anything else to say, Hannah? on that
Uh,
topic?
no, not really. I think that that's
Okay,
about it.
okay. Then maybe we can move on to the complicated thing.
Yeah, the complicated thing. How do we do quantum simulation? So a little bit background. Quantum simulation was actually one of the things that started the whole field of quantum computation. If you have a physical molecule that you want to simulate, what you do is you create a mathematical model. Basically, you have your Schrodinger's equation governing the dynamics for the molecule, and then you discretize it and you try to run it on classical computer. And so these equations, any algorithm that we know so far, and it's been proven theoretically as well, is going to be exponential because of the Schrodinger's equation and because of the way world behaves at microscopic level. You have an exponential scaling, which means anytime you add one or two qubits or particles to the system, the resources required to simulate the system doubles, and hence the exponential resource requirement. So this was like a big problem because for chemistry, this was really important thing. So that's where none other than Feynman himself said, "Hey, I mean, why are you using classical computers to simulate something quantum?" So he just threw out this idea, hey, wouldn't it be cool like if you guys could make a controllable quantum system to which you could map a quantum system that you want to study and then somehow tweak those knobs or create similar environment as to your system that you want to study in the controllable quantum system and study its properties. So he didn't actually propose the quantum computer idea, but he proposed this controllable quantum system, sort of like an analog system. And that gives rise to a field of quantum computer because that's where people started asking, okay, you can create similar environment. What else can you do? And then David Deutsch in 1985 proved that quantum computers could do universal computation. So anything that a classical computer can do, you could do that with this idea of a universal quantum computer. On top of that, you could solve certain problems faster. And this was basically, and then later on, people figured out that Feynman was more or less right, where they figured out there are actually algorithms with which you could map your system that you want to study to a quantum computer, and then come up with algorithms that returns the properties or the things you want to study. Right. Vague intuition why this works is quantum mechanics was the thing that, or the equations of quantum mechanics, Schrodinger's equation, is super hard, and that's what makes it hard to simulate on classical computer. In quantum computer, those same equation or those that exponential scaling come for free, right? And so what happened? There you go. And so the idea is you have a physical molecule, you write down its Schrodinger's equation, which is this, and then in a molecule, the idea is you have kinetic energy of electrons, you have potential energy, and you have Coulombic repulsion. And this is where I'm just gonna breeze through a lot of it. Basically, some equations, and don't worry about it. Basically, all I'm doing is just writing equations, and these are a bunch of, so this is a differential equation right now. So what you do need to do in order to simulate any system on whether classical or quantum computer is you need to discretize. So you come up with a way to discretize it. And so the way it works is you map the fermionic system, which are basically system of electrons or any mass particles. And then you map it to qubits, and then you do the evolution with trauterization, and then you have a bunch of quantum algorithms with which you could read out the energy, right? Wait, I think I have slides in a different order, but this is where the discretization happens. Remember I showed you this differential equation? This goes on to this discretization. And this happens in this step. This step, the first step. And then once you discretize, you're still dealing with something that is different than qubits. So you need to come up with a way to map it to qubits, right? And so you do that, and then you have this variational quantum eigensolver. Now, the idea of the variational quantum eigensolver is it allows you to find the minimum value or minimum eigenvalue of a given operator, which in this case is Hamiltonian. So you prepare an ansatz, you measure the average value of the Hamiltonian, and this ansatz is parameterized, and the optimization of the parameters happen on a classical device, and the measurement of the operators happen on a quantum device, right? And so far, so basically you can think of, we have a quantum algorithm with which you could get the minimum value um, of an operator. And what we want to study for any atom or molecule is the ground state energy, which is the minimum energy that that molecule could be in. So basically, for a lot of the chemistry applications, people are really interested in finding the ground state energy and the energy of the excited states. And with those two energies, they can predict, hey, whether this molecule would react with something else, or if I shine a light on that molecule, would that molecule absorb that light or not? So they can answer a lot of these questions. Yeah, and so basically you have a molecule for which you want to get the ground state energy, which is the minimum energy. So that Hamiltonian, you can think of it as energy operator, which if you input a state of the system, it tells you what the energy of that state is. So if I parameterize that state, which was my ansatz here, I'll be able to get its energy, and then I optimize my parameters in such a way that I get to the minimum, and that's how I retrieve my minimum energy, hence the ground state energy. And so let's see how it works in this in action. What you do is you import a bunch of packages. So you import NumPy, Qiskit chemistry, which is one of the packages that lets you do quantum chemistry simulation on a quantum computer. So you have to import a bunch of stuff and you run it. And then here's where you define your molecule. So let's say I want to study a hydrogen molecule. What I do is I specify H and then its coordinates. So my first hydrogen atom is sitting at 0, 0, 0. My second hydrogen atom is sitting at 0, 0 and 0.7414, which is the equilibrium length of the hydrogen molecule. And then I run a classical simulation. So classical simulation is approximate in nature. So I run approximate classical simulation so that I could get an ansatz which I would know works well. So I do that, I run my classical simulation, I get my one body and two body integrals. So these are some things you get after discretization, rough way to think about these things. And then I get a fermionic operator. So these are the discretized data points you can think of. And then this is my qubit operator. Remember how I was telling you, like after discretization, you are in a still different setting than the qubit setting. So using this piece of code, you transfer your fermionic operators to qubit operators. And let's run this. Running. This is complete. So now you can see, let's see that these are my qubit operators. So these are sort of the operators with which you can construct the circuit for VQE. And once you do that, in order to run VQE, again, bunch of imports and this function so that it could return energy values during each iteration. So that is there. I run that. I run this calculation again. Initial state, bunch of code. And then, oops. And there you have it. So this is basically energy returned after each iteration. So you have your ansatz, you run it, um, run the quantum circuit to get the average value, and you optimize the parameters before you get the final answer, right? So if this didn't make sense, don't worry. Our goal is to actually make something like this available. So in the near future, we'll be making a lot of the apps available where you would just configure you configure the atoms and molecules that you want to run, and we'll generate the code for you, right? So this is something that I want to emphasize. It will also be available as a standalone application. And if you're working on something that plays like a game or something and could work as a standalone application, reach out to us. We'll be happy to make your stuff available in the standalone section as well. Yeah, so that more or less concludes my talk. Let me know if you guys have any questions.
Yeah, I think there were a question. So someone asked, isn't the PDE discrete by nature? Your Hamiltonian looked discrete to me.
No, it was yeah, so at this point, these are operators and these are differential operators. So it's still not discrete. Here, you can argue that it's discrete. So here I've introduced the fermionic orbitals or modes. So your STO3G or what have you. And so at this point, in second quantization, you can think of it as discrete, but at this point, it's not.
All right, I think those are all the questions. So again, if you think of any more questions after the talk, you're welcome to post them in the Discord chat, and Kanav or his coworkers will come by at some point to answer them. And so let's thank Kanav again for his wonderful talk, and hope to see you guys in the challenge. And if you're interested, please submit a project to the QBraid challenge. And also, if you're interested in any of the learn QBook or even research, feel free to reach out to Kanav. I've posted the email address in the chat earlier. If you need it again, we can post it in the Discord again. So yeah, once again, let's thank Kanav for the wonderful talk.
My pleasure.
And so the next event, I believe, is the social. So please head over there if you have time. And yeah, we look forward to seeing everyone in the hacking event on the weekend.
All right.